Hello dear viewers, you are most welcome to Lead 2 Mathematics channel, and thanks for watching. If you are new to this channel, please kindly subscribe, hit the notification button so that you are notified whenever I upload a new video. Like and share. And on this channel we present mathematics content in form of lessons, worked out questions, mathematics challenge. So it's a kind of education channel. So please, today we are diving in the second lesson, rather presentation about vectors, and please endeavor to watch up to the end, like and share. Let's now dive in. Last time we talked about the introduction to vectors. So whichever you see that is ticked, we finished. So we finished vector representation in presentation 1. If you didn't watch it, please, it is there. I'm going to leave the link of the playlist in the description. You tap on it and watch. We also talked about vector classification. We talked about operation, that is addition, subtraction, and scalar multiplication on vectors. We talked about how to get the magnitude of a vector, midpoint of a vector, and then equal vectors or equality of vectors. Now in this presentation, we are going to talk of the following. We are going to talk about parallel vectors. For these ones, let me take a tick on the left hand side. So after talking about parallel vectors, after understanding or talking about parallel vectors, we shall also talk about collinear points. We shall talk about proportion division of a line applying vectors. So we shall talk of this specifically so that we can understand them. So now let's dive in. We have parallel vectors. And what are parallel vectors? We are saying that parallel vectors are vectors which can be expressed as a scalar multiple of the other. So when given two vectors, for example, if you have vector A and vector B, and we have some constant k, or the scalar, then we can express vector A in terms of the other vector, which is B, by a scalar multiple. And we are saying that diagrammatically, these vectors that are parallel can be represented as you can see in this diagram or illustration below, whereby you have vector A taking this direction, it is taking that direction as you can see. Then vector B is also taking the same direction, and we are saying that these two vectors are parallel and they are also running in the same direction. That's why we have the vector A being expressed as a scalar multiple of vector B, and we can see that the scalar is positive. The reason why it is positive because both two vectors are parallel and they are taking the same direction, or they are running in the same direction. It is here, as you can see, you are saying that both vectors, vector A and vector B, run in the same direction. That's why we can have our constant being positive. Let's look at where they run in opposite direction even when they are parallel. So we are saying that if a scalar k is negative, then it reverses the direction of vector B, like the way we have seen from the earlier on illustration. But still, this vector is parallel to vector A. So we are saying that in case one reverses the direction, we shall then have vector A being expressed in terms of vector B as being equal to the negative, the scalar, multiplied by vector B. And still we are saying diagrammatically, they would appear as we can see below here. Vector A, we can see it is running in this direction, whereas vector B is running in the opposite direction of vector A. And by expressing these vectors, we've seen that vector A equals to the negative k vector B. So they are parallel, only that they run in opposite direction. So having talked about that, let's proceed with example. Let's have examples here. They are saying that given that P, point P 11, Q 34, R 85, and S 62, show that PQ and SR are parallel, and deduce that P, Q, R, and S are vertices of a parallelogram. So they are asking us to show that these two vectors are parallel, and again we go ahead to show or to deduce that these points P, Q, R, and S are vertices of a parallelogram. But before that, this is a vector. So they are showing us to show that the vector PQ, then vector SR are parallel. So what we are going to do, we are going to have the response here, well written, and let's follow together. We are having our point P, which is 1, 1. So we can now change all of these ones to position vectors, whereby for point P, we are going to have our position vector OP, for O being the origin, being equal to 1, 1. Then position vector OQ is equal to, it's going to be 3, 4, in form of a column vector or position vector. Then vector OR, position vector OR is equal to 8, 5. And position vector S or S equals to 6, 2. Now from this step, remember we are required to find or to show that PQ, vector PQ and vector SR are parallel. So let's first get vector PQ and vector SR respectively. So let's get vector PQ. So vector PQ is the same as we begin with this vector OQ or vector Q. So it's same as vector OQ, same as position vector OQ minus position vector OP. So as we substitute in here, we are having vector OQ as 3, 4 minus vector OP, which is 1, 1. As we simplify this, is the same as having 3. Let us subtract the corresponding components. So we have 3 minus 1. Then we have 4 minus 1. As we simplify this, the same as having vector PQ being equal to, so 3 minus 1 is a 2. Then 4 minus 1 is a 3. So we are having our vector PQ being equal to this. Also, let's find, so we say also vector SR is equal to the position vector OR minus the position vector OS. Now let's substitute in. This is equal to vector OR is 8, 5 minus the position vector OS, which is 6, 2. As we simplify this, we are having our vector SR being equal to, so we subtract the corresponding components. We have 8 minus 6, then 5 minus 2. As we simplify this, we are getting our vector SR being equal to, so 8 minus 6, we have a 2, then 5 minus 2, we have a 3. So we can see that our vector SR equals to 2, 3. So we can compare. Remember, we got our vector PQ as 2, 3. And again, we are getting our vector SR as being 2, 3. What does it imply? So we are saying that also vector PQ, we have got it to be 2, 3. From this, what can we deduce or what can we observe? As we see that these vectors are the same, it implies that we can express these two vectors in terms of the other, implying that our vector PQ equals to vector SR. And in here, it means that these two vectors are parallel, and our k is 1. So there is a 1 there. Our k could be, our k equals to 1. Can conclude and say therefore vectors PQ and vector SR are parallel vectors. So you are saying that they are parallel because vector PQ equals to the scalar multiple of vector SR. They say that hence deduce that PQ, R and S are vertices of a parallelogram. So what you're going to do here, remember a parallelogram, it can be of this form, like the way I'm drawing it here, it can be of this form. So we can have our point P, Q, S, and then our R. So if this is now the parallelogram, and we observe that the vector PQ is equal to vector or is parallel to vector SR, implying that maybe vector PS should also be equal to or should be also be parallel to vector QR. And also we are going to find out whether vector PS is parallel to vector QR or the other way around. Then from there we shall go ahead and get the magnitude of vector PQ, whether it is equal to the magnitude of vector SR, and also whether the magnitude of vector PS is equal to the magnitude of vector QR. Then from that we shall deduce that the points are vertices of a parallelogram. Let's do it. So in here we are required also to go ahead and find or show that the vector PS is parallel to vector QR. So let's see. Let's begin by getting vector PS. is the same as the position vector OS minus position vector OP. So by substitution, vector OS is the same as 6, 2, as you can see from here. Then vector OP is equal to 1, 1. As we simplify this, we are having the 6 minus 1. We are subtracting the corresponding entities, and then a 2 minus a 1, implying that our vector PS equals to the 5, 1. So also we are required to go ahead and find vector QR. So vector QR equals to position vector OR minus position vector OQ. So let's substitute in. Position vector OR is given by 8, 5. So we are having 8, 5. Then position vector OQ is given by 3, 4. So minus 3, 4. As we simplify this, the same as 8, 5 minus 3, then 5 minus 4. So implying that our vector QR equals to, so 8 minus 3 is 5, then 5 minus 4 is 1. So we can see that also vector PS equals to vector QR, implying that they are also parallel vectors. Parallel vectors. So from this, we can go ahead and be getting the magnitudes. So let's first find the magnitude of PS or PQ. Magnitude of vector PQ is going to be equal to, remember the formula is the square root of x squared plus y squared. But our vector PQ is given by, we can cross check, vector PQ is given by 2, 3. So it is 2, 3, whereby x equals to a 2 and then y equals to a 3, implying that the magnitude of vector PQ equals to the square root of the 2 squared plus 3 squared. This gives us the square root of 4 plus 3 squared is 9, implying that we have the square root of 13 units. So the magnitude of vector PQ equals to the square root of 13. Let us also go ahead and get the magnitude of vector SR. So the magnitude of vector SR is going to be equal to the square root of, but vector SR, can see vector SR is also 2, 3. So let's substitute in. So equals to 2 squared plus 3 squared, implying that we have also the magnitude of vector SR being equal to the square root of 13 units. So we've seen that the magnitude of vector PQ is equal to the magnitude of vector SR. So meaning that those sides are equal. Let us also go ahead and calculate the magnitude of vector PS and also compare it with the magnitude of vector QR. So the magnitude of vector PS is going to be equal to, remember our vector PS is 5, 1, it is here. So it means that we are going to have the square root of 5 squared plus 1 squared. So this gives us the square root of 25 plus 1. And this is the same as having the square root of 26 units. So this is the magnitude of vector PS. Let us also go ahead and find the magnitude of vector QR. So the magnitude of vector QR, remember vector QR was equal to vector PS. So equals the square root of 5 squared plus 1 squared, implying that the magnitude of vector QR is so equal to the square root of 26 units. So we can deduce that therefore points of vertices P, Q, R, and S are vertices of a parallelogram, because vector PQ is parallel, so is parallel to vector SR. Also vector PS is parallel to vector QR, and the magnitude of vector PQ equals to the magnitude of vector SR, and the magnitude of vector PS equals to the magnitude of vector QR, as we have seen. So that is how we could conclude. There is this trial question. It is here. It reads, given that A is that, B is that, C is 6, 5, D is 2, 5. Use vectors to show that vector AB, to show that vector AB is parallel to vector CD, and that A, B, C, and D are vertices of. So try it and drop your findings or your answer in the comment section. Let's now jump over to collinear points, having talked about parallel vectors. So what are collinear points? We are saying that Collinear points are points that lie on the same line, as you can see in the illustration here below. And we are saying that the idea of parallel vectors may be used to test if any three given points are collinear. So we have to consider that, put it in our minds and understand it. So we are saying that consider 3 points A, B and C. So for us to show that points A, B and C are collinear, we have to also show that the vectors AB and vector AC are parallel. So if vector AB and vector AC are parallel and are taken with respect to a common point A, so we can see that we have AB and AC. So we check whether they are parallel and they are taken from a common point, which is point A. So then points A, B and C are collinear. So we can have the first example. We have number 1. It reads the coordinates of PQ and R are 1, 2, 9, 2, 5, 2 respectively. Then find vector PQ and vector QR and show that points PQ and R are collinear. Let's now have our response. So the response is gonna be here. Let's go through it thoroughly. So from this, according to what we have learned from the collinear points, we should get vector PQ and compare it whether it is parallel to vector PR, but not vector QR. So implying that we are going to get vector PQ and relate it with vector PR and check whether they are parallel. If they are parallel, then we shall say that points PQ and R are collinear. Let's now proceed. We have been given points. So points P is 1, 2, implying that our position vector OP equals to 1, 2. Our position vector OQ equals to 9, 2. Then our position vector OR equals to 5, 2. So as proceed, let's get vector PQ. Vector PQ is the same as position vector OQ minus position vector OP, implying that we have our OQ is 9, 2 minus our position vector OP, which is 1, 2. As we simplify this, we are getting our vector PQ being equal to 9 minus 1 is 8, then 2 minus 2 is 0. So that is our value for vector PQ. Then vector PR, the same as position vector OR minus position vector OP. So as we substitute in, our position vector OR is 5, 2 minus our position vector OP, which is 1, 2. As we subtract, we are getting our answer for vector PR being equal to 5 minus 1 is 4, then 2 minus 2 is 0. So we can see that our vector PQ is 8, 0, then our vector PR is 4, 0. So our vector PQ equals to 8, 0 and our vector PR equals to 4, 0. So let's try to see whether we can express these vectors in terms of the other. So vector PQ equals to the 8, 0. So let's pull out a 2. So we have vector Q equals to the 2 into 4, 0. But vector 4, 0 is the same as vector PR. So vector PQ equals to twice vector PR, implying that these two vectors are parallel. Therefore, we can deduce that therefore points P, Q and R are collinear because vector PQ and vector PR are parallel. So this becomes our answer. So we have talked about, so far we have already talked about parallel vectors and then also collinear vectors. Let's now talk about proportional division of a line. That's number 10, proportional division of a line. So we have part A. They are saying that internal division of a line. Consider the line segment AB below, as you can see, and being divided into 6 equal parts. So you can count them. They are 8, they are 6. So they are saying that point C is such that it is 2 units from A. We can see that point C is 2 units from A, from here to here. And it is 4 units from B. It is 4 units, 1, 2, 3, 4 from B. The ratio of vector AC to vector CB is equal to 2 to 4, i.e. So we are saying i.e. that is to say vector AC, the ratio of vector AC to vector CB equals to 2 to 4. As we reduce this, because there is a common factor of 2, we are getting the ratio of vector AC to vector CB to 1 to 2. And we are saying that the point C is therefore said to divide the line AB internally in the ratio of 1 to 2. Then let's look at when the point is dividing a line externally. That's point P. So B, we are saying that consider the figure below where AB is produced to point C. So where point C is produced as a result of extrapolating this line AB, extending this line AB to C. So we are considering point C here, and it is outside the internal line AB. As you can see, it is outside AB. So we say that it is external. It is external. So AB is divided up into 6 equal units. And say 1, 2, 3, 4, 5, 6, and BC is equal to 3 of those. So taking the direction from AB as positive, then C to B is negative. Thus we are going to have our vector, our ratio of vector AB to vector CB being equal to the 9 units, goes from here to here to C there 9, to, since it is dividing it externally, to negative 3. As we simplify this, is the same as vector AB divided by vector CB, which is equal to the 9 divided by negative 3, implying that our vector SC AB divided by vector CB equals to 3 divided by negative 1, implying that the ratio of vector AB to vector CB when C is a point dividing the line AB externally equals to 3 to negative 1. So as you can see below here, we are having that in this case we say that C divides the line AB externally in the ratio 3 to 1, or simply C divides line AB in the ratio of 3 to negative 1. Let's have examples. Example 1, they are saying that the coordinates of E and G are 2, negative 1 and 6, 7 respectively, given that 3 vector EG equals to 4 vector EF. Determine EF and hence the coordinates of F. So let's have our response. So our response is here. So we've been given that 3 vector EG equals to 4 vector EF, implying that since we want to get vector EF, it means that we can put it on the left hand side. So we have 4 vector EF being equal to 3 vector EG. We can make a vector EF a subject by dividing through by 4. So it means that we have vector EF being equal to 3 divided by 4 vector EG. But what is vector EG? From the coordinates given, we can see that the position vector OE equals to the 2, negative 1, and the position vector of OG equals to 6, 7. So now from this step, let's substitute in. It means that from here, our vector EF, which we want, equals to the 3 divided by 4 into our vector EG, same as position vector OG minus position vector OE. So as we substitute, we are getting 3 divided by 4 into position vector OG is the same as 6, 7 minus the position vector OE, which is 2, negative 1. Implying that we have 3 divided by 4 into, so 6 minus 2 is 4, then 7 minus 1 is 6. As we multiply, we are getting our vector EF being equal to, so 3 divided by 4 multiplied by 4 is the same as 3, then 3 out of 4 multiplied by 6, we are getting 9 out of 2, implying that our vector EF equals to 3, 9 out of 2. This is our vector AF. We also say that hence determine the coordinates of F. So we go ahead and determine the coordinates of F. From here, we need to first find the position vector or F before getting the coordinates of F. So from vector EF, this is the same as the position vector OF minus the position vector OE. But the position vector OE is the same as 2, negative 1. From the equation here, you can see it is 2, negative 1. So it implies that our 3, 9 divided by 2 equals to, because our vector EF is that, equals to position vector OF, which we are looking for, minus vector OE, which is 2, negative 1. So let's make EF the subject. It means that position vector OF equals to the 3, 9 out of 2 plus vector 2, negative 1. So position vector EF OF, so equals to 3 plus 2 and then 9 out of 2 minus 1. So as we simplify this, we are getting the position vector OF being equal to, so 3 plus 2, we are getting 5. Then 9 divided by 2 minus 1 is same as, so the LCM is 2. So we have 9 minus 2. As we simplify this further, this is same as having vector 5. Then 9 minus 2 is 7 out of 2. So this is the position vector EF, implying that the coordinates of F equals to 5, then 7 out of 2, or 3.5. So therefore, the vector EF equals to 3, 9 out of 2, and the coordinates of F are 5, 7 out of 2. So this becomes our answer for this number. Let's have another example is here. So you try out this example 2, which reads, given that B is that 12, 3, and C is negative 3, 12. Find the coordinates of E such that the ratio of vector BE to vector BC equals to 2. Try it out and drop the answer in the comment section. And thanks for watching. See you again next time. We shall begin on geometrical vectors. See you again in the next presentation. Goodbye.